thank Samuel for organizing the nice conference and nice dinner and excursion yesterday. So I'm Remy Belmonte, so I'm currently a PhD student at University of Bergen. And I'm going to talk about finding contractions and induced minors in chordal graphs. So in this talk I will essentially focus on contractions. I will briefly mention induced minors in the end. So this is a joint work with Peter Golovac and Daniel Brusma from University of Durham, Pinar Heganes and Pim Farnetov from University of Bergen, and Marcin Kamiński from University de Bruxelles. So first, let me remind you of what most of you already know, actually, probably. So what an edge contraction is. So you choose, you have a graph, you choose an edge, you delete the two vertices incident to this edge, and you replace them by a new vertex whose neighborhood is the union of the neighborhood of the two vertices you just deleted. So these two vertices are adjacent to three vertices, so the new vertex is adjacent to the three vertices. So now we can define a problem which is called H-contractibility. So you are given a fixed graph H and an input graph G, and you want to decide if you can obtain a graph H by contracting edges of G. So for instance, this is your graph G, this is your graph H. You can contract first this edge, then this one, then the last one, and indeed you end up with a graph which is the same as H. So the graph G we had in the beginning was indeed contractible to H. So just something I had to say. So in the later in the talk I will use little n to denote the number of vertices of H and of G, and little h to denote the number of vertices of H. So this is the usual way of seeing H contraction, but there is another way which are called witness structures. So we say that G and what we call an H witness structure of a graph G is a partition of the vertices of G into disjoint non-empty sets. Each set of vertices must be connected. Each set also corresponds to exactly one vertex of H, and there are edges going between two sets if and only if the two corresponding vertices in H are adjacent. And these sets are called witness sets. So now what is known about the problem H contractibility? So first, it has been known for quite a long time that this problem is very hard. So even if the graph H is very small, like a path on four vertices or a cycle on four vertices, the problem is already NP complete. But on restricted graph classes, there are some positive results. So it has been shown recently that the problem can be solved in polynomial time on planar graphs, or also on chordal graphs when the target graph H is either a split graph or a tree. And split graphs are the graphs whose vertex set can be partitioned into an independent set and a clique. So both these classes are subclasses of chordal graphs. And what we show now is that you can extend this result in the case where H is basically any graph. So actually you can restrict yourself to the case where H is chordal, because if you contract edges of a chordal graph, you end up always with a chordal graph. So first let's start with something a bit simpler than chordal graphs, namely interval graphs. So what we are going to look at is, so we are going to assume we are given H and G, and you assume G can be contracted to H. And then the question is, what does your H witness structure, any H witness structure of G will look like? And in particular, what will a witness set of this witness structure look like? So interval graphs are hereditary, so this the subgraph induced by a witness set will be an interval graph. And in particular it will have a leftmost interval and the rightmost one. So these two intervals we call the boundary of the witness set. And I mentioned earlier that every witness set is connected, so there must be a path between these two yellow vertices. And also the witness structure is a partition of the vertices, so every vertex must belong to a set. So in particular all the black vertices here they lie completely, and these yellow vertices are the leftmost and rightmost intervals, so every black vertex here in the witness set lies completely between the yellow vertices. Yeah, so this holds for every witness set. And as I said, the witness structure is a partition of the vertex set of G. So every vertex belongs to exactly one witness set. So okay. So now the question is, how do you turn that into an algorithm to decide H contractibility on internal graphs? So essentially, what you will do is you guess the yellow vertices. There are exactly 2 of them for each witness set. So you have 2 times little h yellow vertices. So you have n to the power of 2 times little h choices. And then what you want to do is you want to find this disjoint path, because essentially if you have them, then you're done, because you know that every remaining vertex, it will fit somewhere. It will fit in some witness set. Because if there is a black vertex which does not lie between 2 yellow vertices, then it basically means that your choice for the yellow vertices was not the right one, because by definition of the yellow vertices. And so now what you have is you guess your yellow vertices, and for each pair of yellow vertices you know exactly which vertices are allowed to be on the path between them, because these vertices are exactly the one lying completely between the yellow vertices. And also you don't a black vertex can if a vertex is not yellow, it can possibly belong to several it could, in the end, ultimately it will belong to only one path, but it could possibly, it is allowed for several paths. For instance, I don't know, maybe this interval here, it could be here, and it could be somewhere here, and it could be allowed to belong to this witness set and this witness set. So now for each pair of vertices, you have a set of allowed vertices, and you want to find disjoint path which use only vertices in this set of allowed vertices. So now we can define the problems, which we call set restricted K disjoint path. So you have pairs of terminals. In our case, it will be these pairs of yellow vertices. The domains. In our case, for each pair of yellow vertices, it will be the intervals lying completely between. And then you want mutually vertex disjoint path between the pair of terminals, using only the vertices from the domain. So the bad news is that this problem is already NP complete when you just ask for 2 pairs of terminals on general graphs. But the good thing is that we can actually solve it in polynomial time for fixed K on Chordal graphs. And from what I just said, you should already see the next one coming, which is that we can solve H contractibility in polynomial time on interval graph, because we try every choice of yellow vertices, and then we solve the instance of set restricted K disjoint path we get out of this choice. And the graph G is H contractible if and only if there is one of these instances which is a yes instance. So now we can go to Chordal. So in the end you get n to the big O of h, which is polynomial because h is fixed. And now we can go to Chordal graphs. And what I claim is that essentially what I said for interval graphs will also kind of hold for Chordal graph, and it will be essentially almost all we need to get it. So Chordal graphs are graphs without induced path of length 4 or more, but that's not very convenient for us. So what we will consider is that Chordal graphs are exactly the intersection graphs are subtrees of a tree. So you are given a ground tree, and you take induced subgraph of this ground tree, and 2 vertices in your graph are adjacent if and only if the associated subtrees of your ground tree overlap in some vertex. And so now, as I said, what we would like to do is basically the same as for interval graphs. So we look at at some H witness structure of some Chordal graph G. So what does it look like? So you have a bunch of subtrees of your tree. So in this case, it's a bit unlucky because there is our only path, but they could be trees. Anyway, and we would like to do the same as previously, which is we would like to guess some boundary and then find some set of vertices that would make the boundary connected. And hopefully, we hope that it would be the only thing we need to do. So first, we need to explain what this boundary is in the case of chordal graphs. So essentially, it will be that you take a leaf of your ground tree, and the boundary of one witness set for with regard to this leaf is the vertex of your ground tree which is closest from this leaf and which contains vertex of your witness set. So basically you take your witness set and you try to go as far as you can in the direction of this leaf, and you do that for every leaf, and with this you get some boundary. The small problem is that so for integral graphs we just had two directions. We could just go left or right, but in the case of chordal graphs we have a tree, so we can go in many directions, and actually there are bigger of n such directions. In the worst case, the number of leaves of your ground tree can be quite large. It can be arbitrarily large compared to the size of H. And since we would like to guess just the boundaries, we cannot afford to guess things in. We cannot afford to guess bigger of n things. So we need to bound the number of leaves of the ground tree. So fortunately, this holds for every witness set. And fortunately, so we can bound the number of leaves of the ground tree, kind of. So what we can do actually is we say you start from your ground tree, and I will not explain how, but you can basically just make a bunch of new graphs such that each of them have at most little h leaves, and you have big of n to the h such graphs, which is polynomial once again because h is fixed. And the good thing is that your initial graph G can be contracted to H if and only if one of these graphs can also be contracted to H. So from now on we can assume that we work with a graph which has at most little H leaves. And so now we are almost back to we have something quite similar to integral graphs. The only difference is that for integral graphs we wanted to guess disjoint path. Now disjoint paths are not exactly enough. We need actually disjoint trees, because in the worst case you could have, for instance, some boundary here, and then you would need maybe some tree instead of a path. And once again, the good news is that and once again the good news is that we actually can. So we're doing almost the same as for disjoint paths, so except that now we call it vertex disjoint trees. So instead of pairs you have sets, you still have domains, and you ask for trees once again instead of path. And we can solve this problem in n to the liter of p time, where p is basically the total number of vertices you have here. And the reason why it's good for us is that here we will have at most, since we have bounded the number of leaves, we will have at most little h vertices in each of these sets S1 to Sk. So, and we will have exactly one such set for each witness set, and we have exactly little h witness sets. So we have p bounded by h squared. So we can solve this. So the instances of disjoint path we get here. So yeah, once again, I forgot to say how we define the domain. It's the same as for integral graphs. So you just take the trees which lie completely within your boundaries. And so now we indeed have an instance of restricted K disjoint tree, and we can solve this problem in n to the h squared time. And once again, because of this and what I said previously, we get that we can solve H-contractibility on chordal graph. So this is the kind of detail loading time almost. So this is for the this is because of this. So we created a lot of instances, so we have to solve contractibility on all of this problem, on all of these instances. Then this is the number of guesses we have for the boundaries, since each boundary contains at most little h vertices, and we have little h boundaries. And this is the time we need to solve the instance of restricted k-disjoint tree we get. And this is roughly n to the h squared time. And once again, it's polynomial because little h is fixed. So I promised I would talk a bit about induced minor. So induced minor is H contraction, and you are also allowed to delete vertices. And there's a nice result which gives us everything for free, which is that if you are given a graph G and H, you can H is an induced minor of G if and only if a graph H prime is a contraction of G prime, where basically you get the prime graphs by adding a universal vertex. So basically, yeah, we get H induced minor can be solved in polynomial time on Chordal graphs because of that, because you just take your graph G and H for the prime induced minor, you add the universal vertex, and you solve H contractibility on these two graphs you get. So yeah, so since there's the open questions just afterwards, I will kind of start with my questions. So what we saw once again is that you can solve this promise in polynomial time. The question is, can you do FPT time if you parameterize by the size of the target graph? But unfortunately, actually no. So that's not a question. Because it's these two problems are W1 hard on split graphs, but still you can work on a different question, which is so you don't have hope for Chordal graphs, but maybe for interval graphs you can get rid of the part where first you would need to get rid of the guess when we guess the boundaries. And also you would kind of need to get rid of the fact that so we have n to the k time for the disjoint path, and can you get FPT running time parameterized by the number of terminals? On Chordal graphs, it could still be true actually, or even on interval graphs. So yeah, I don't know if it's a good way to do it, but yeah, maybe trying to get rid of the guess, the part where we guess the boundaries, and then trying to solve this in FPT time. Hopefully you could solve the whole thing in FPT time. And so I guess that's it. Thank you very much.